looking at structure bound noise in the last class. And we said that structure bound noise we usually take care of by providing isolation, for those sources whose frequencies are known. For example, for a machine we know the RPM, and it will be imparting the force at that RPM. So, in a way we know the frequency of the forcing function, the one which is actually causing vibration of the structure. So, we actually provide isolation in between, and let us say this is our machine mass is somewhere here, machine mass is somewhere here, this is our machine mass, and we have a force, because it will be periodic rotating machine mostly or reciprocating machine. So, they will exert periodic forces. So, force should be something one can express possibly in terms of some sin omega t, and this is my mass of the machine, and isolator I put in between, this is my floor. So, this isolator actually what it does? It does not allow all the vibration or all the forces to be transmitted here, all the forces to be transmitted here. It reduces down the force, and the decibel we can define transmissibility in this in some manner, the amount of force that will transmit, and this is the forcing function which has got an amplitude of f0 and then varies sinusoidally, because it will be 0 at some time and then go to the other direction and so on and so forth. So, this is the isolator, this is the mass. Let us say I do not have the forcing function now and I have put the isolators, the mass would be there. This mass results in some sort of static deformation or static deflection of the isolator itself, which might be something like a spring, right, spring or similar sort of system. The idea is that if it is a spring, it stores the energy, a spring will store the energy and release it. Now, it stores the energy, the moment the energy comes from here, it stores this energy, and then sometime releases with kind of a phase lag or time lag, releases here, some amount gets attenuated and also releases at certain with some kind of a time lag or at certain time later. So, therefore, finally, it results in a kind of a vibration of the floor or foundation u0 sin omega t. So, there is a force here would be u0 sin omega t. So, that is the idea, that is how we actually stop structure bound noise, particularly coming out from machine or similar sort of thing, whose frequencies are known. For those ones which are random type and whose frequencies we do not know, we handle them in a slightly different manner, we will see that later on. So, through isolation, that is transmission of vibration from machine to building is prevented. Now, such a system can be modeled as a mass and spring system that I have just shown you, the single degree freedom system, neglecting damping. There will be some damping, some loss of the energy, right, some loss of the, for example, it can be it could be some kind of viscous damping. The energy is now actually transmitted in a way, energy is some energy will not be transmitted, because there is some viscous damping can occur, in the sense which is generally proportional to velocity, right, which is proportional to velocity, or as you know, viscosity is related to deformation rate, therefore, it is proportional to velocity, and the force is actually proportional to, or stress, shear stress is proportional to velocity gradient, as we have seen earlier from definition of viscosity. So, there can be some viscous damping or loss of energy, etc., but we are neglecting that in this particular case, because we are considering the simplest of all cases, right. So, this is how system can be modeled, and this is the mass, this is my spring and this is my foundation. So, spring equation we know, mass into acceleration, if y is a displacement along this direction. So, y is the acceleration, y double dot is the acceleration, must be equals to spring stiffness, because you know the force in a spring is proportional to the displacement, and this is the equation of spring that you would be knowing. and therefore, if I look at this equation, and if you remember, the auxiliary equation will be d square plus k is equals to 0, because it is m k by m y double dot plus k y equals to 0. So, y double dot is simply is equals to k by m y equals to 0. So, this is my auxiliary equation, right, and root of this one will be simply plus minus under root k by m. So, solution would be simply e to the power plus k by under root k by m plus e to the power minus under root k by m a plus something like a plus b, as you know, that will be the solution of y, right. So, this we discussed something similar earlier, because we know, just for those of who still do not recollect your solving basic maths, is exponential function is one which if you differentiate again it will come back. So, if it is y dot sum a y dot plus b y is equals to 0, simply if you it is the type of function which will satisfy that kind of equation is exponential, and if it is double dot y double dot e to the power minus x can also, if you differentiate it twice, it will come back to the same one again. So, y double dot sum m y double dot plus k y. So, and the to the solution would, you can show that very easily, that complex root it would be, because it is a minus under root k by m. So, under root I under root k plus m, and solution of this one comes out as a cos k by m t, b sin k omega k by m t, right. And if you differentiate it, a and b will come from the boundary condition, because y double dot is involved. So, you to solve that, two constants of integration will come if you are integrating them. Therefore, from the two boundary condition a and b can be solved. So, you can see that cos function, if you differentiate it once you get sine, and again you differentiate you will get cos back again. So, and similarly sine is so on. So, that is how it comes, and you must have looked into this solution. So, initial condition t equals to 0, y is equals to y 0 and y dot is equals to 0, that is initial condition. Spring has deflected, static deflection, somewhere it has deflected to y is equals to y 0, and velocity is equals to 0. Now, supposing I consider the spring without the mass and just pull it a little bit. So, y 0 is the initial, I am only looking at the property of this isolator right now, right, there is no force. So, I just pull it y 0 to y 0 and release it. So, at time t equals to 0 y 0 and release it, velocity is 0 at that point, and if I solve this, put this here, when t equals to 0, this term becomes 1, right, cos 0 is equals to 1 and this term is 0. So, y is equals to y 0, therefore, a is equals to y 0, because this would be 1 a, this is y is equals to this, y is equals to all this, and this term goes to 0. So, when t equals to 0, y 0 is equals to a. So, a equals to y 0, and if I differentiate it, then I get y dot. So, this will become sine, this will become cos, and y y dot is equals to 0 at t equals to 0. So, therefore, b must be equals to 0, that will satisfy, because b, this will become cos after differentiation, right, after differentiation this will become cos. Y dot, if I y is equals to a cos under root k by m t plus, so y dot will be a sine something, this one, and multiplied by this factor coming outside. Similarly, this will become b cos function of t after differentiation y dot, and therefore, when I put t equals to 0, b under root k by m, this term under root k by m will always be there here. This will be cos under root k by m t, sine if you differentiate you get cos you differentiate you get minus sine. So, cos you differentiate, this will become sine actually, so if I differentiate it. So, when t equals to 0, this term goes to 0, this term will be 1, but y dot is equals to 0. So, therefore, this is the situation. I mean, is there any problem in this? It is pretty simple. There is no, let me just do it again if you are not comfortable. Let me just do it again. Let me just do it again. I am saying y is equals to a cos under root k by m t plus b sin under root k by m t, that is right. So, if I differentiate it, I get y dot is equals to a minus s under root k by m sin under root k by m t plus, am I right? Is it okay? Cos under root k by m t, and here again you will have under root k by m, right, under root k by m. Is that correct? There is any problem in this? So, when I put t equals to 0, this term goes to 1, this term goes to 0. So, my b and all this k under root k by m is not equals to 0. So, b must be equals to 0, b must be equals to 0, that is how I am getting it, that is how I am getting it, right, that is how I am getting it. So, therefore, you know, a equals to y dot 0, b equals to 0. So, finally, y is equals to y 0 cos, because a is equals to y 0 cos under root k by m t. So, if you know this is, I have not put any load or any force onto this isolation, and this is nothing but omega. So, if I pull this isolation, put it to some value y 0, and there is no damping, then it will vibrate from y 0 to y 0, its displacement will go from y 0 to minus y 0 and omega t. So, it will repeat itself after, this is omega 2 pi, you know. So, this is basically omega. So, this is the natural frequency of the system. This is the natural frequency of the system. I have taken only the spring, and spring will, right. So, k by m, if I put in a mass and then I have started causing the mass, just pulled it up to y 0, leave it, you know. So, just pull the mass a little bit and leave it. So, for that system, the machine I have pulled it and then left it, no forcing function, I have not applied any function, then it will vibrate at with this natural frequency, right. So, it will vibrate with this natural frequency or angular frequency, and natural frequency is f n. So, vibration of spring is simple harmonic with k by m as angular frequency, under root k by m as angular frequency, and at when I have just put in the machine, it deflects by delta, spring, you know, static deflection deflects by delta right in the beginning. So, mass into mg must be equals to k delta, because I said that I have put in the machine and then pulled it up. The system is mass, then the isolation, then my foundation. So, there is an initial static deflection whenever I have put it. So, that is called static deflection, and m by k or k by m is g by delta, right. So, omega by n g by delta, that is equals to twice pi f n. So, twice 1 by twice pi, you know, f n k you can get it by 1 by twice pi under root k by m, etc., and delta is in millimeter. So, one can find out the natural frequency of the isolation and the machine put together, right, isolation and machine put together. So, that is the system. When the machine is operating, it imparts vibration to isolation periodically, that means it applies a force, and then equation becomes something like this, because earlier there was no force, I have just pulled it up and it started moving about its mean position of equilibrium, machine plus the isolation together. Now, I have just started forcing it, the machine is on and it forces continuously, imparts force onto the isolation. So, periodicity of the machine, this is the periodicity of the machine at which it applies force, and this you can solve by through particular integral, you know. solve through particular integral. So, y is equals to, this will be the particular integral for this particular this specific case, a sin omega t minus phi, because if you put this here and differentiate it twice, if you put this one, because it has to be a sine or cos function, or like exponential which will repeat itself. So, here it will be sine or cos function. For this kind of sinusoidal function, particular integral is of this kind. If you differentiate it twice plus k y, if you put it, and right side put f 0 equals to sin omega t, you will get the value of a. Differentiate it twice multiplied by m, then k multiplied by this. If it is this, put equals to this, then you will get the value of a. So, if you do that, for y is equals to differentiate, so differentiate it twice, you will get sin first omega t. So, omega comes and again differentiate it, you will get sin back, minus sin is cos and cos is minus sin. So, you will get a, first time you differentiate this, you will get a omega cos omega t minus phi. Again you differentiate it, you will get a omega square, and it must be multiplied by m, and then k into this only, k into this is equals to f 0. So, I can evaluate a out of this, I can evaluate a out of this. So, if I take a common from this 2, I get m omega square plus k sin omega t, and right hand side also f 0 sin omega t. So, a at phi is equals to 0, if at when there is a the phase angle is 0, it is because its starting point could be different, its starting point could be different. Phi 0 means its starting point is different. If you remember when we talked about that, it's in times one wave is following the other, let us say. So, this should be in terms of some phi. So, if at phi equals to 0, a equals to f 0 k m omega square, and k you remember was related to omega n square, because under root k by m is equals to omega n, right. So, k is nothing but m omega n square. So, k, this is k and there was m here. So, I can take m out. So, it is something like this. So, a is this, and general solution therefore would be y 0 cos omega n t, that is for the natural frequency part of it, and this is because of the forcing frequency, right. So, what we are saying is that we assume that they are in phase. When they are in phase, that is the worst situation, and f 0 omega n minus omega sin omega t. So, when this is natural frequency part of it, but when these two are same, omega n and omega is same, then this term becomes infinity. That means, displacement tend to become very large, because this is a small portion compared to this, and when both of them are in phase. So, forcing frequency and natural frequency they are in phase, then you get resonance will occur. That means, it will have very high amount of vibrations transmitted through. So, we define a function called, or rather a parameter or property of the isolation, which we call force transmissibility. Like transmission coefficient we talked about transmission, transmission loss was 10 log 1 by tau. So, where tau was transmission coefficient, transmission coefficient. Here we define something called, because it is not force per unit area, we are not dealing with pressure. So, we talk in terms of force transmitted divided by exciting force, f 0 sin omega t, and how much is transmitted, u 0 sin omega t or whatever it is, that we define as tau, and tau is simply then k y divided by f 0 sin omega t, right. F 0 sin omega t, the force that is imparted, and k y will be the displacement of this isolator, which will be transmitted to the, is a spring. So, that is the force it will transmit to the foundation or the base or the floor foundation, because whatever K y is the force in the spring, that would be transmitted to the floor. So, K y divided by F 0 we take modulus. So, maximum force transmitted will not involve complementary solution. So, we forget about the sin omega t, because that will be small natural frequency part of it, and therefore, we write it simply this part, we take this part only, and maximum force transmitted would be given by this. So, which is simply coming out as, this will cancel out with this. So, I left with K by m omega n minus omega n. What is K by m? Omega n square. This I can write, all neglecting damping and all that, this I can write as 1 divided by, divide everything by. So, it will be 1 omega by omega n square, omega by omega n square, right. So, tau is given by 1 by 1 minus omega square by omega n square, or the difference one can take in both sides, and we define transmissibility as tau, and 10 log or 20 log 1 by tau will be, because 10 log pressure square was there. So, 10 log force square. So, here 20 log 1 over tau will be the delta dB, 20, because we are talking in terms of force, like pressure square was there. So, force would be also square. So, 20 log 1 by 20, and this will be delta dB. So, if you can see that if these two are same, then tau becomes infinity. So, this is the point, this is the ratio of forcing frequency and natural frequency, omega, forcing frequency omega n by omega, here it is forcing frequency is omega by omega n, and when this is equals to 1, the transmissibility is maximum. If this is the ratio is quite large, then transmissibility reduces on both the sides. So, here also it reduces when the ratio is small. So, therefore, and corresponding dB you can find out, because supposing it is 1, 20 log of 1 is equals to 0. So, force transmissibility in this point, if this essentially if transmissibility is 1, tau is equals to 1, delta dB is equals to 0, and on this direction it increases. So, here this ratio transmissibility is, when this transmissibility is 0.2, that is 1 by 0.2, delta dB is more, it is inversely proportional to. So, as this value is smaller and smaller, delta dB noise reduction increases. Noise reduction increases as this value becomes smaller and smaller, because delta dB is this. So, we try to keep this away from the natural frequency, forcing frequency. So, natural frequency of the isolator should be 3 to 4 times than that of, yes. So, choose the isolator accordingly. This is the simplest of all these structural dynamics or vibration equation, simplest case we are talking of. So, simple isolator, because we want to reduce down as much noise as it is. So, for known omega, decide omega n for given dB reduction. For known omega m, determine isolation from graph or from equation. You see, this graph gives us, for example, it gives us natural frequency versus static displacement, or simple 15.76 under root, that 1 by delta, the formula that I gave you earlier. So, one can determine from this, remember this formula we talked about, or this is given in National Building Code. This was given in National Building Code, or anywhere you can actually, you need not look into the code, but look at the material, and for the given load. So, delta is the static deflection, given machine weight, how much is its static deflection of the isolator, which could be a cork board, could be a neoprene rubber, or some kind of system, depending upon whatever it is, right. So, find out if under the static load how much delta it would be. So, you got to know its k value in a way, that should be known to you, and this will be the natural frequency. Now, forcing frequency of the machine you know. So, the ratio now you can choose. So, what should be the F n you can find out, because you know F omega by omega n, that is same thing, omega by omega n is same as F by F n, and delta dB is known to you, right. Therefore, how much ratio you should maintain you can find out, because delta dB is equals to 20 log 1 by tau, and tau is equals to 1 by tau is equals to delta dB 1 by 1 minus this ratio. So, this ratio you can find out depending upon delta dB, and this is known to you. You find out F n, choose an isolator which will have deflection required for F n, because F n is equals to this deflection. So, under the machine load the deflection should be this. You can choose materials like, as I am showing you, materials like cork board, materials like steel springs are somewhere there, rubber 15 centimeter thick, cork board, etc., etc. So, this would be steel spring, typical spring should be something of this kind, rubber 15 centimeter thick, they show static deflection under per kg or whatever it is known. So, different boards, then cork board, then felt. So, specific material that you are using, its thickness, how much will be its static deflection for the given machine load, that you can find out, right. So, let us go back to this equation. So, I can find out tau, how much, first I know tau, I will find out from this equation. Let us say I want 20 dB this. So, corresponding to this tau will be equals to, corresponding to this log 1 by tau will be equals to 1, right. So, how much is tau would be, how much the tau would be, this this is equals to 1, which means that 1 by tau is equals to 10, am I right. 1 by tau is equals to 10, NT log of 1 is how much, 10. So, 1 by tau is equals to 10, that means tau is equals to 0.1, tau is equals to 0.1, and for tau is equals to 0.1, how much is this ratio you can find out either from this curve or straight away you can find out for 20 dB this 0.1, right, and you want this much, then the ratio should be 3. But then no, these days nobody looks at the curve, because you do in Excel calculation or somewhere else. So, 3 times your natural frequency ratio of these two should be, forcing frequency by natural frequency should be 3. So, choose the natural frequency of the system F n accordingly. Then for this machine load F n is equals to 15.76 1 by delta. From the set of materials that is available, cork with different thickness, maybe spring, rubber, whatever it is, if there are 4 springs in parallel you can find it out, all this I do not think I will go into that details, but this is from basic school physics you can find out and determine the isolation, right. So, that is how we take care of machine noise or noise with known frequency, because f must be known, forcing frequency small f or omega must be known to me. If it is unknown, which can happen, so let us we will look into that. It can happen, for example, just for sake of example, footfall noise, kitchen noise, utensil falling, these are random noises, there are no machines, right. So, if there is a kitchen, there would be noises generated and they are random. I mean, let us say a hotel kitchen and first floor, right, or somebody say some workshop, some of them might be dropping something or doing some work onto the some work onto the floor or similar sort of thing. So, why do you expect random noise? You do not know the omega value, you do not know the natural frequency of the system, I mean sorry, forcing frequency you do not know. So, you have to then think it in different terms. We will look into that in the next